All right, let's get started for today. Do we have any questions before we get going? Nothing? All right. So today we are going to cover electromechanical systems. But even before we do that, we're very briefly going to review our mechanical systems, specifically for rotational or torsional mechanical systems. So, same chart we've been doing for the last week or so. Our element, our diagram, or our figure, the parameter, dynamic state, stored energy, and our relevant equations. All right, we're going to do this for rotational systems. Mechanical systems that rotate. Or torsional. So what we got? What are our three passive elements for rotational systems? Nope, we're not in electric. That's electromechanical. Motor is electromechanical. It's the second part of this class. Simpler. Passive elements, right? So think about what we did with translational mechanical systems. Think about what we did with electrical circuits. I should give you a hint. So a spring, right? Or torsional spring. That's one, right? And so I will draw that either just like a regular spring, or sometimes it's a bar and I'll put like a spring constant next to it. Either one of those are okay, right? What do we think the parameter is for a torsional spring? What was it? K or KT, as I sometimes will use a subscript for that. And that is Newton meters over radians in this case, right? Our dynamic state or our stored energy, either one of those, what do you guys think that would be for a torsional spring? Right, what type of energy will we be dealing with here? I heard somebody whisper it over here. Potential energy, right? And so what do you think that would have the form of here? Going off of what we have already. One half MGH for a spring. 1/2 KT, even though sometimes I'll just use K. And what do we think? For a spring, that's like its elasticity is fighting us when we're rotating it, right? Theta, what does theta represent? Like the angular displacement, right? Angular deflection, right? So theta squared here. So what does that mean our dynamic state would be? That'd be our net angular deflection, which is theta. That's in newtons of radians, typically, right? Relevant equations. What were our relevant equations with our translational mechanical systems? And how can we move them to this world? All right. What was the name of one of them? Had a specific name to it that you guys should know by heart now. Hooke's law, right? So what do we think Hooke's law is going to look like for a rotational system? So Hooke's law says force is equal to K times deflection, right? What is it going to say in this case then? K theta is equal to what? So you're saying it's equal to force, right? I don't want to use force here. Torque, right? So the torque of our spring is equal to that spring constant times theta, right? If you want to convert it to a force, you could. But we're going to, with rotational systems, deal with our torques. The other equation, right? It's the rate of change of our deflection would be the sum of the angular velocities of each end, right? Or omega net, right? That's our spring. So that's our first element, first passive element. What's the second one? What is the units of theta times r? So theta is in radians, right? Right. And then r is in what? Saying like meters, right? Okay. So then what would the units end up being then in that case for torque? Would that be what a unit of torque is? No, right? That'd be a force, right? We have taken the r, moved it over to the other side, taken force divided by r, right? And that's our torque, right? That's where it's coming from. Okay. Second passive element. What is it? Damper again, right? Which I'll represent as this, or sometimes I'll just do like a box with an X in it that's connected somewhere, kind of representing like a brake. Its parameter is going to be that damping coefficient, Newton meters seconds over radian. What type of energy do dampers store? None, right? And so we don't have a dynamic state associated with them. And so our equation for dampers with translational systems was force is equal to that damping coefficient times velocity, right? So how about we do that in the rotational world? The torque from a damper is the damping coefficient times, we'll say the net angular velocities. Same parallels here, right? We're seeing a pattern between all our systems. Yes. Newton meters seconds over radians. NMS over radian. Other questions? All right, last element. These two are the easiest ones. Last one's still pretty easy. So it's like a mass. I don't want to say mass itself. I'm going to say inertia. All right. Usually I'm going to represent it as like a disk or something like that. Sometimes I'll even represent it as like a bigger, thicker disk. All right. Inertia, we're going to say that parameter. I'm going to use J here. You guys have probably used I or different things here, but we're going to keep it pretty simple and always use J. J has units of kilograms meters, right? And so what type of energy do we think a disk that's spinning is going to have? Kinetic energy, right? What do we think kinetic energy is going to equal to in this case? One half omega squared J, right? Something like that, right? Same pattern that we've always had, right? So what is our dynamic state going to be? Thing that's associated with energy changing in an inertia? Was it? Omega, right? Our angular velocity. Omega. Units of radians over seconds. All right. What is our big relevant equation? The name of it or the equation itself for our inertias? Any ideas? How about someone online? Let's go with that. Folks online, what is our relevant equation for an inertia? Folks online, can you hear me? M omega double dot in the right direction here. Good. Anybody want to help this person out? J alpha, that's kind of the same thing here, right? Along the same lines, right? I is L over, what is I over L omega? I'm guessing that's what that is. There's 3 people that said that. Does anybody know what the context of that is? I over equal L over omega. I have no idea where that's coming from. You guys are gonna have to explain that to me one day. L is angular momentum. Okay, now we're getting not quite. All right, somebody in class, let's help out the folks online. They at least tried. And I'm seeing some of the right elements here. All right, what was the thing that we used for masses? Give me the name of what it is. Do you know the name? Newton's second law, right? What do we think it's going to be for our inertias, rotational system? Still Newton's second law, right? We're just going to be using slightly different units, right? What do we think the torsional equivalent? I'm starting to see representations that look very similar to mine, right? Newton's second law would say our mass equivalent, J, right? Our inertia, times, you guys would say alpha, I'd say the rate of change of angular velocity, right? Is equal to the sum of our moments or our torques. Not momentum. Momentum is a little bit different, right? Looking at moments, or I usually go with torques, just to kind of distinguish it here, right? Same exact equation. All right, so these are 3 passive elements here. Instead of force, we have torque, tau, which could be an input for this system, right? And the modeling procedure that I would recommend for these would be the exact same thing that we've done before for mechanical systems. So let's go through one example. And we'll probably save the second example for at the end of class, or I'll upload it online if we don't have time for it. So I'll draw out an actual spring this time. The spring is connected to some sort of inertia. I'm not drawing very well here. This has an inertia J. We have a spring constant KT here. This is a wall, showing that that spring is going to twist on this end here, but it's locked into place over here. All right, let's actually also add in a damper to our system. You can think of it as like kind of like a brake that's always applying to this mass trying to rotate around. All right, and we also have a torque applying to our system. I want our output is going to be our angular deflection. I should say our net angular deflection of the spring. And we also have zeros for our initial conditions. All right, this is a system that we're working with here. So how do we get a transfer function from our input to our output? Right, so this is an external torque that's acting on our system, right? It's driving our motor to turn. All right, so how do you guys want to approach getting a transfer function for this? Yeah.
Just to make sure the damper is there at the bottom.
Think of it as like it's a wheel and it's like brakes are applying onto it. Yeah. It doesn't, the location of the damper doesn't matter. It's applying onto the inertia. That's it. I could have drawn it over here. I could have drawn it on top, wherever.
It's going to be on the wheel.
It's on the wheel, right? Yeah. That's how I'm drawing it in this case. We could have it somewhere else, but usually I try and just put them directly on our inertias themselves. All right. So we want to get a transfer function for this system. You guys lead the way with this. Laplace transform. You want to start off with a Laplace transform immediately? I don't think a Laplace transform of this is going to work. Not immediately, but maybe we will use that eventually. All right, a free body diagram. Let's start with that. So free body diagrams would be for our inertias. Okay. And so you guys tell me what forces are acting on this. Or anything else you want to tell me about the free body diagram. Oh, you started, I think. I can't hear either, you guys. Torque, the which torque? The applied torque? This torque? So we're just going to draw that one again. Okay, sure. That's one of them, right? That's our external torque, right? That's our control input, right? So maybe we should identify that as such. Okay, well, what directions are those going to go? Choose one. Counterclockwise for which one? Spring. I'm going to draw it here. Okay, and what's that torque amount? PT what? Which one? How many say omega? How many say theta? It's a spring, right? KT theta. Here's the thing though. Where's theta? All right, we never actually drew theta anywhere on here, right? I need some sort of like to know which direction theta should be, right? What is positive theta? What is positive omega? How are you guys choosing it? Which direction? You guys are going with direction of the torque. So this is theta. All right, what about omega? Same direction? Sure. It doesn't matter. You just need to be consistent here, right? That's the key. But you guys haven't actually defined theta yet, so we might as well do that. Mm-hmm.
The way so we have to be consistent, does that mean like the direction of theta has to be the same direction as omega?
I would recommend theta and omega to be in the same direction if possible, right? But that's not always going to necessarily be possible, right? One example I can think of for that, we have an inertia. I have a spring here and a spring here, right? And then I have a torque that's going this way, and then another torque going this way. How do you choose your thetas here to be appropriate, right? You got to think about these things. And maybe this is even connected to another inertia over here, right? You guys are defaulting to going in the same direction as the applied torque, and that's okay in this case. But be aware that there are situations where that's not always going to be appropriate or the easiest way to go about doing it. Okay, so we got KT times theta, right? What other torques do we have acting on our free body diagram? What direction? I've heard a lot from you, so let's go with somebody else. I've also heard a lot from you. Damper. Okay, where's it going? What direction? Clockwise or counterclockwise? Counterclockwise. And what's that torque going to be? What was that? CT. Now, is this omega or is this theta? This one's omega, right? Okay. Any other torques that are acting on our system here? Are we all good? Okay. What else? What do we guys want? What we want to do next year? What? Dude, you're whispering, man. Equilibrium? Sum of the forces in each direction equals what? It's like you're getting quieter, man, as you go along. right? It's not equilibrium. If it was equilibrium, this would be 0, right? We're just applying Newton's second law. J omega dot, right? If it was equilibrium, there's no derivatives with respect to time. Right? These forces are not necessarily canceling each other out. Right? We do have some motion. So J omega dot is equal to what? Just read it out for me. Is that right? Based off of our sign convention, is this correct? This has to be negative for all of them, right? What direction is positive omega? Right, that's clockwise, right? So any clockwise torque is going to be positive. Any counterclockwise torque is going to be negative. You got all your signs flipped here, right? This would say if you want to apply a torque of a certain value, right, it would spin in the opposite direction. Doesn't make sense. At least based off of these definitions that we're going with here. Okay. What else? Other ideas? Right, the input-output equation somebody wrote up there. Maybe not a bad idea, but how do we get there? Okay, so what's that relationship? Theta dot is equal to omega, right? So therefore, omega dot is equal to theta double dot. You can do it this way. That's one option. Okay. All right. From here. Yeah.
Make sure I'm understanding the question. So there's an applied torque, spring and damper on the existing one, that's what.
Yeah. If a damper and a spring didn't resist that torque, but instead went along with it, right? Wouldn't that be a problem? Right? If I started to spin a wheel and friction added energy in that direction, right? It would just keep spinning faster and faster, right? Even if I never put in any more energy, right? The spring and the damper, as long as they make physical sense, want to stop that motion, right? So it's whatever the positive omega direction is, or the positive theta direction for the spring, right? They want to stop that. They want to return back to their equilibrium, to their rest. Spring wants to go back to its original position, right? Doesn't want to have any potential energy in it, right? A damper doesn't want any movement whatsoever, okay? All right, from here, we're getting close now. Laplace transform. Now it's time for the Laplace transform. Second order derivative, two S's. We already said, should use the capital theta here. Try and draw it out. Something like that. I think there's bars or something. First order derivative, just one S, and we don't have any initial conditions, as we said earlier. Okay. Our final steps. All right, transfer function, what is our input? Input is U, right? Control input, right? It's that torque. I gave that to you guys earlier, but you're going to need to be able to identify that in the future. There's a torque floating out there and it doesn't have any equation it depends on, probably an input. What's our output? theta, right? Okay, so you guys tell me, what is y over u, which in this case is theta over u? And it should look familiar, right? We just move all the thetas to one side, combine those terms together, divide by that, divide by u. We should end up with 1 js squared plus cts plus kt, right? Looks really, really similar to a lot of the different equations that we've actually done already, right? We've seen this almost exactly in translational mechanical systems, ms squared plus cs plus k, right? We've even seen it in our electrical systems, but I think we had a 1 over c floating around somewhere. Right, but we had something on the order of ls squared plus rs plus 1 over c or something like that. All right. So this is just a very basic example, but you guys should be able to do a little bit more complicated versions of these things here. One last thing I want to touch on for translational or rotational systems is our gears. Right. Gears are like inertias that don't have any inertia, right? So we can make some approximations about their dynamics. And the way I'm going to do gears in this class, I'm going to keep it pretty basic. Instead of dealing with number of teeth and all that sort of stuff, I'm just going to say the gears have certain radii, R1 and R2. This is theta 1. This is T1 or tau 1. This is tau 2 and theta 2. Right? And gears, I'm sure you guys all know these formulas already. Tau 2 over tau 1 has a static relationship, which is R2 over R1 in the lossless case. These are lossless gears with zero inertias to them. And then we also have theta 2 over theta 1 is R1 over R2. And then, of course, we also have, very similarly, omega 2 over omega 1 is R1 over R2, right? If we have time, we'll go through an example with a gear. If not, I'll post one online. But you guys should all be pretty familiar with these equations, right? But all of these, the gears themselves, actually can come from Newton's second law in our inertia cases. And looking at the forces at the point of contact, right? And there's a special case where that J theta double dot ends up being 0. But they don't have any J to them. All right, any questions on rotational systems before we start shifting into our actual topic for today? So now let's talk about electromechanical systems. What's a good example of an electromechanical system? Somebody said it very early in the class. A motor, right? What's another example? Starter? Getting close. Yeah, it's close. Engine, not quite here. Very similar to a motor, but like the opposite. Generator. We're going to model both of these as the same thing. In this class, we cover DC motor / generators because a motor and a generator, for our purposes, are the same thing, just one is running in the reverse direction as the other. All right. So the key to motor operation is magnetic coupling, right? And let's say we have some sort of like conductor, like a wire, and it has current going through it. All right. So let's say we have this wire here. Right. We're applying a voltage across these two ends of the wire, right? And we're going to get a current, little I here, that's going to run around this wire. Right. This is all our current I. Then we have, let's go with I don't know, blue, I guess. We have a magnetic field running across this, right? This is a magnetic field. with flux density B. All right. And what the basics of motor operation say, there are two rules. The first rule says that magnetic field exerts a force on the wire, the conductor, right? Where that force is direction is determined by the right-hand rule, right? So essentially the relationship between the direction of current and the direction of that magnetic field. So in this case here, let's go with purple, I guess. In this case, over here, because of this current and this magnetic field, using the right-hand rule, we get a force pointing up, trying to rotate the wire this way. Over here, because the relationship between the current and the magnetic field is the opposite, it's trying to push it down over here, right? This is our force F, right? Our force F is equal to, and this is like very simplified dynamics for motors, right? The magnetic field's flux density, B, times the length of the wire, times that current. All right, what this says, in a nutshell, is that the force produces the current existing is going to produce a force acting on the system, right? And if we had these two ends over here pinned down, it would be a torque, right? It'd be rotating around, right? We have one side being pushed up, one side being pushed down, right? That is the basic operation for how motors work. Right? What this says is that we have that electrical power, that voltage that was applied over here that was generating that current, right? And that is being converted into rotational power, right? Mechanical power. Right? The second law that we have is that the field induces a voltage in the wire, in the conductor, that opposes the voltage producing the current. Right? This is specifically for a conductor moving relatively in a field here. What this is called is our back EMF. VB is equal to B times L times V, where this is the velocity of the wire. Right? And we can actually see from this relationship, if I were to take that system and start to spin it myself physically, right? That back EMF would generate a voltage, generate that current that's going to go back and turn mechanical power into electrical power, right? That's our generator mode, right? These are our two principles, the primary ones for how motors work in a very simplified manner is what we're covering here. Okay, you guys should be relatively familiar with this. So let's just push on ahead to modeling a DC motor. Right? DC motors have two parts, right? There's a reason why these are called electromechanical systems. We're going to have an electrical part and a mechanical part. The electrical part, I'm going to simplify down to the armature circuit. Has to deal with our rotor coils. And so we have our armature voltage, VA, or our input voltage to our system. And the insides of a motor on the electrical side boil down to a resistor. I'll call it RA here, but sometimes I just call it R or RM, and an inductor. And then due to that second law there, we're going to have a back EMF this back voltage that's going to fight against VA here. Right. This is 1/2 of our motor circuit here. So let's use time domain methods this time. And I just want to at least start getting the equations here. We're eventually going to get a full transfer function, but I just want to get like the big equation, the important equation from this circuit. Anybody have an idea how to get that? What do we need to do? Resistor and inductor, okay. What kind of, how do you want to approach this? Kirchhoff voltage, you could just call it the voltage law, right? Okay, so you want to use the voltage law here? That makes sense to me. What's the voltage law state? Zero is going to be equal to something. What's the everything? You don't write what you're saying literally. Somebody help him out. Total voltage, you're saying the same thing he is though. Give me specifics. Okay, give me specifics. What's I? Where? I don't have that here. So we need to probably label that current, right? All right, so let's put that current there. Okay. RA times IA, right? What else? That's the important one here. Okay, plus or minus. All right, probably would help if we define what our voltage signs are here, right? Okay, what else? We all good? All right, that's our back EMF, and we're going to leave that as this for now, right? This is our voltage law. Don't forget to label things, right? Or at least when I'm going to play dumb up here and not tell you, just assume you guys know what's going on here. Right. So I could also rewrite this as IA dot. It's going to be 1/LA VA minus RA IA minus VB. Okay, that's the electrical half of our motor. Then we're going to have the mechanical half, which is going to be an inertia. Right, that's J. We get the torque from the armature circuit. Sometimes I'll just write this as tau. Sometimes I'll write it as tau A. Sometimes I'll write it as tau M. Let's pretend for now that we have a load torque fighting against our motion here, right? This could be a brake. It could be something else in our system, right? Or outside of our system, rather, I should say, right? So what would be the primary equation for this guy? What do we want to work with here? We just did this, right? But this is easier. Second law, right? So what's the second law going to state here? Okay, where's omega dot? Clockwise or counterclockwise? Clockwise. I would prefer clockwise here, but you could do counterclockwise as well, right? Okay, and that's going to be equal to what? Tau A minus tau L, right? Torques that are going in the positive velocity direction, torques against it, right? The easier version of what we did earlier. Okay. All right. So now we need the critical part here, these are just two separate systems up to this point, right? The critical part with our motors is that motor torque is proportional to what? What was it proportional to? Based off all our discussions before. I wouldn't say current input in here, but the current going through the armature circuit, right? So motor torque is proportional to armature or the electrical half's current, right? And using the equation that I wrote up before for force, I'm going to convert it into this torque here, where we're going to have N times B L times IA, right? That was our force that we had before, except this is just number of coils. And the rest is exactly the same as that equation. We want to convert it into a torque here, multiply by R. I'm just going to group up this and this together, and I'm going to call this KT, or sometimes I'm going to call it KB or KV or KM. I'm very inconsistent with what it is. This is not a spring constant. This is our motor constant for our system. So what does this say? It says the torque from the armature circuit that is going to be driving our physical or our mechanical part of our system is equal to some constant times the current going through that circuit. We get more current going through our circuit, we're going to have more torque out of our motor. All right. Our other half, our back EMF, that back voltage, relates to what? What is that proportional to? A key thing in here that's going to be changing over time. Our velocity, right? So VB our velocity would be R times omega here. We can go through everything, but VB is N VL V, or we can simplify it down and it'd be Km times omega. Right? It is the same exact motor constant that we had for torque, right? The same exact constant determines how much back EMF we have and how much torque we have. Right? That is our constant that relates to the transfer between electrical and mechanical energy. Question? Number of coils. It's not going to be relevant for you guys. I'm just going through the derivation a little bit more detailed. It's just saying how many times the thing wraps around. We had the length of the wire multiple times. All right. Now, the key with the motor here is that we have our two equations, this guy and this guy, but we need to plug in these other terms here. So IA dot, or I could say LA times IA dot, was equal to VA minus RA IA, right? Minus VB, but VB is Km omega, right? That is VB. And suddenly, we now see an electrical circuit dynamics that depend on something in the mechanical world, right? That omega term there showing up. Similarly, J omega dot is tau A minus that load torque there, but tau A is Km times the current, right? And now we see a mechanical system that depends on something electrical, right? These two equations here are what we're working with for our motor, right? Probably would be good to be familiar with this setup in general for our motor dynamics. I would especially encourage you guys to memorize our formula for tau A and VB. Make sure you know those, right? Because you don't want to spend time looking them up. All right, so now we can get a transfer function, right? our inputs to this system, VA, right? That's an external torque or an external voltage source, right? That's putting power into this system. That's one of our inputs. But we actually have another input, right? This load torque, right? That is an external torque that's acting on our system here. So we actually have two inputs. Let's say U1 is equal to VA. U2 is equal to that load torque, right? And I want our output to be, let's just go with our angular velocity. That's a typical output for a motor, right? Where we can convert it into an actual velocity if we want to multiply it or divide it by or multiply it by radius. All right. So with this set up here, let's get our transfer function. Got our equations. What do we do from here? I want a transfer function. Let me specify. I want y of s over u1 of s here. Okay, so we do a Laplace transform of all of these equations, really, I guess, right? So LA S IA of s here is going to be u1 of s minus RA IA of s minus Km omega s, right? Laplace transform of our second equation. This is our Laplace transform. Do the same thing over here. JS omega s Km times I of s minus U2 of s. What do we do from here? Pretty straightforward, right? Mm-hmm. Yeah, there's one extra piece here that we also need to do, right? But I agree, I would probably solve this for IA of s, right? And that'll be in terms of omega, because omega is the one we're looking for, right? And then we would plug it into our second equation. What's the other thing we would need to do here? Simple. What am I looking for? The transfer function from u1 to y. What's the last thing that we need to do here? Get rid of u2. So u2 will be 0 for the transfer function we're looking for, right? And you can go through and solve this, and you would end up with, I think, KB over JLA times S squared plus JRA times S plus KB squared. I'm just skipping ahead of my notes here, but I think it'd be something along those lines. What term? JRA. But you guys should go through and practice this on your own. All right. I think we're just about out of time. Any last minute questions? Oh, KB is KM. Like I said, I switch between all of them all the time, right? I will try and be consistent in the homework. Why do we zero out U2? Because we're looking for the transfer function from U1 to Y. And if we have multiple inputs or multiple outputs, we can only have a transfer function from one input to one output. The rest go to 0. Or the rest of the inputs, I should say, go to 0. All right, that is it. Don't forget about homework. Number 2 is due on Friday. And I'm going to post some additional examples online, or at least one for the gear example. But that's it for modeling. Next time, we're going to go into first and second order systems. KB squared. right. I'm gonna. Can you post an example of the electromechanical system as well? We just did it. And so the video will be uploaded online, and so you'll be able to go through that. In addition, I think there are some of my videos I've discussed about earlier in the semester. If you go to my lab website, I think there may be an additional electromechanical system too. Otherwise, wait until the homework. That'll be another one.